So we are going to continue with the pre-calc review stuff, and then we're going to talk about how to find derivatives of these things and all that. Very likely that there may be a multiple choice question tomorrow on the AP exam involving a derivative of one of these things. Well, we're taking care of it. What I would like you to do, I think we've finished everything on page 2, I believe. Remember, the whole point of inverse trig is these questions are asking us to find the angle whose sine is something, whose cosine is something, and all that stuff. But the answers need to be answers in a particular quadrant. When we're giving an answer to an arcsine, an arctangent, or an arccosecant problem, remember we need to give an angle in quadrants 1 or -1. Don't tell me 11 pi over 6, tell me negative pi over 6. And when we're dealing with an arccosine, arccotangent, arcsecant problem, we are giving answers in quadrants 1 and 2. Hopefully this is kind of sounding familiar from Friday. Hopefully, maybe. Top of page 3, you're going to try those 6 evaluating problems on your own. There are a few things that are a tiny different than what we looked at, but see what you can do. We'll talk in a little bit. If you feel like you want to have your filled-in version of the blank unit circle out, you're welcome to take that out. When we get to a quiz on this stuff, I can certainly give you blank copies of the unit circle, but not with the angle and sine and cosine. That's a little bit confusing. When we will get to a quiz on the inverse trig stuff, there will be some of this pre-calc stuff on there before the derivative work. So I do need to make sure you know how to evaluate and can give an answer in the right quadrant. I'm not totally sure what to do with like this one. We'll talk in a moment. The last one, I don't feel like doing the last one anyhow, the way it's written. If it was me, I'd change the problem into something else and then do some work with the stuff inside. And make sure you're paying attention to those quadrants. Just a single number answer. Make sure for arcsine, arctangent, arccosecant, you're in quadrants 1 or -1. For arc cosine, arc cotangent, or arc secant, all the things kind of based on cosine, you're in quadrants 1 and 2. Maybe one more minute and then we'll start to talk. Let's start to look at things. Jacob, what did you say for the arc sine of root 2 over 2? Good. We're looking for an angle in quadrants 1 or negative 1, whose sine is root 2 over 2. Well, I know it actually has to be 1, because in quadrant negative 1, the sines are negative. Pi over 4. Katrina, how about the inverse cosine of negative a half? Good. We're looking in quadrants 1 or 2. I know it has to be quadrant 2 because that's where the cosines are negative. Where the cosine, the x-coordinate around the unit circle, is something is negative 1/2, and it's going to be 2 pi over 3. Anyone have a thought on how we could deal with that arctan of root 3 over 3? That doesn't look great to me. Marcus. Okay. So first of all, this thing, I'm not actually going to write this on here because I'm going to run out of room, but this actually came from rationalizing the denominator, the root 3 over 3. Well, I could kind of unrationalize my denominator if I wanted to, just to kind of see like what it came from. Could multiply by root 3 over root 3. Guess we can call this rationalizing the denominator. No, rationalizing the numerator, rather. We'll get 3 over 3 root 3. We'll get 1 over root 3. That looks a lot better. Still not totally good. Marcus told us what to do with that in a moment. But I'm going to rewrite this problem as the arctangent of 1 over root 3. And again, Marcus, what did you say? Good. I like seeing the 1/2 root 3 over 2 things rather than just a 1 and a root 3, because those are the values I see around the unit circle. So now, I'm looking for a place in quadrants 1 or negative 1, where the sine is a half, and the cosine is root 3 over 2. Pi over 6? Sure, at pi over 6, things will work. Eric, thoughts on that next one, the inverse cotangent of negative root 3?
It's going to be root 3 over 2 over 1/2.
Okay, so let me start by doing that. Inverse cotangent of, I'll just stick the negative out front, root 3 over 2 over 1/2. Good.
It's negative, so it'll be in the second quadrant.
Good. I'm looking for quadrants 1 or 2, but it's a negative thing, which means one of the sines or cosines has to be negative. That's going to be quadrant 2.
And I have 2 pi over 3.
2 pi over 3? Yes? Good? No one's saying anything. Do we like 2 pi over 3, or do we not?
No.
Okay. What would you prefer?
5 pi over 6.
Okay. What do you think about 5 pi over 6? No? Okay. So I do like 5 pi over 6. I'm looking for something in quadrant 2 where the cosine is root 3 over 2, where the sine is 1/2, and one of them is negative. I think the cosine is going to have to be the negative one because we're moving to the left to get to quadrant 2. That is going to be 5 pi over 6. Next, the arcsecant of negative 1 is like asking what angle has a secant of negative 1. I never like doing secants or cosecants. Rather than asking what angle has a secant of negative 1, Marcus, what question should we ask? Sure. What angle has a cosine of 1 over negative 1? Which is really just saying, what's the arc cosine of negative 1? Heidi, what is the arc cosine of negative 1? What angle has a cosine of negative 1? Pi. Good. I want quadrants 1 or 2. That's quadrant 2. Angle's pi. Similarly, I don't want to do the last problem. I don't want to find the inverse cosecant of 2 root 3 over 3. I don't want to ask the question what angle has a cosecant of 2 root 3 over 3. Kristen, what question would I rather ask myself?
The inverse sine of 3 over 3.
Good. The inverse sine of 3 over 2 root 3, which does not look great to me. Rationalize the denominator. I think you are going to get a good-looking thing inside your sine there. Rationalize the denominator. We're going to get the inverse sine of 3 root 3 over, okay, root 3 times root 3 is 3 times 2 gives me 6. Oh yeah, this will become good. This is really just the inverse sine of root 3 over 2. That is something good. What is it?
That would be pi over 3.
I agree. Answer to that one, pi over 3. And I feel like between these and the ones we did last time, I kind of showed you all the different tricks that could occur when you're dealing with these problems. There's only so many options because there's only so many numbers we're dealing with. If you got something like arctan of root 3 over 3, the denominator was rationalized. Let's unrationalize the denominator, rationalize the numerator, and then see if we can get our 1/2 and root 3 over 2s. I never want to do arcsecants or arccosecants. I'd rather do the arcsine or arccosine of the reciprocal of the thing inside. You'll try a few of those in the homework. Last two topics we have to deal with from pre-calc. Composition problems. Evaluating things when we have a trig function inside of an inverse trig function. Well, I'm just going to kind of start on the inside and work my way out. The arcsine of the sine of pi over 6 is the same as saying the arcsine of, well, what is the sine of pi over 6?
1/2.
It is 1/2. And my problem is now, don't shout out the answer, think for a moment, and I'll call on someone in a minute, is figuring out the arcsine of 1/2. What angle in quadrants 1 or negative 1 has a sine of 1/2? Okay, now raise your hands. Kristen. Pi over 6. And the answer to this is pi over 6. Yeah, they just cancel each other out. So the answer is pi over 6. Wouldn't it make sense that inverse trig should cancel out trig? Eric, what did you just kind of say a moment ago?
It depends on the quadrant.
Aha. In this case, they cancel each other out. In general, they may or they may not cancel each other out because we can do trig functions of any angle. But when we do an inverse trig function, the answer has to be in a particular quadrant, which may not necessarily be where the original problem happened. I think this next example will show that. The arcsine of the sine of pi. Well, what's the sine of pi? 0. Now, I want an angle in quadrants 1 or negative 1 whose sine is 0. They didn't cancel each other out, giving us pi. The reason they didn't cancel each other out, giving us pi, was because pi was not an angle in one of those quadrants 1 or negative 1 thing. Give me like 2 seconds. Like really 2 seconds, don't go anywhere. I can't really bother remembering when it cancels, when it doesn't, so I would just sort of start on the inside and work myself out to figure things out. Try the bottom one while I go see what Mrs. Thompson wanted. Inverse tangent of the tangent of pi over 6. Is the answer 5 pi over 6? It is not. Okay, So I'm going to start. Inverse tangent of, okay, 5 pi over 6. The sine is a half. The cosine is root 3 over 2. You know what? I'm just going to kind of leave it like this since I kind of like the 1/2 and root 3 over 2 thing while I look around the unit circle. I think the sine's a half, and the cosine is negative root 3 over 2, and I'm just going to stick the negative out front. Quadrants, what are we looking for? What quadrants? 1 or negative 1. Which one are you really focusing on? Okay, what do you think? I think negative pi over 6. I think when you're at negative pi over 6, the sine is negative a half. The cosine's root 3 over 2. Yeah, we'd get that thing just with the sign on the negative sign on the top part rather than the bottom part, but that doesn't really matter. I would not bother just kind of canceling these things out. I would just start on the inside and work your way out. If the angle wasn't a good quadrant, they'll cancel. If it's not, you have some other work to do. Totally different, though, if we have trig functions on the outside and inverse trig things on the inside. What this example on the bottom of the page is asking us is the arc sine of 3/7, find the cosine of that, which is really like saying, what angle has a sine, we're not going to use a calculator for this in a moment, what angle has a sine of 3/7, find the cosine of that. I think I actually want to write down that question. What angle has a sine of 3/7? I don't know, but once I do know, I'm going to find the cosine of that angle. Do you know what angle has a sine of 3/7?
No, I'm not saying
I feel like if I asked you a half, or root 3 over 2, or 1, you can handle that. You can't handle 3/7. Here's the trick. What angle? I'm going to say that the angle is some random angle theta. And I'm going to draw myself a triangle. And I'm going to put in a theta. I have no clue what theta is, but it's not really going to matter so much. The cosine of the arc sine of 3/7. I don't know what theta is, but I know that the sine of theta is 3/7. If the sine of theta is 3/7, what sides of the triangle do I know?
Oh, no, the hypotenuse is 7, and the opposite side is 3.
So, katoa, OH. I know my opposite is 3. I know my hypotenuse is 7, so I'm going to fill those things in there. My opposite is 3. My hypotenuse is 7. I bet you can find the adjacent. Take a moment to do that. And simplify it. Then we'll go and we'll actually try to answer the original question involving inverse trig inside trig. It is a simplifiable side. No, we will not. Root 40, so I think you should be getting 2 root 10. And I think it's 2 root 10.
Oh, I see. Never mind.
Sure, it's your root 10. So, I don't actually want theta, though. I wanted to find the cosine of theta. Could you look at that triangle and tell what the cosine of theta is going to be? How are you getting that? The adjacent over hypotenuse. That's what we're going to need to do. What angle is the sine of 3/7? I don't know what the angle is, but I can draw a picture of an angle whose sine is 3/7. That's what I did over there. Then I want to find the cosine of that angle. Again, I don't know the angle, but I don't really care. I can still find the cosine of the angle because I have my picture of the triangle. Does that make some sense?
Will we ever have to, like, do, like, with the 3 that we just did, where
Yes.
it's in the wrong quadrants, will that ever be in the wrong quadrant?
Let's move on to the next one. I think that'll answer your question. Sort of in the wrong quadrant. The next one, we want to find the cotangent of the inverse secant of negative root 5 over 2. By the quadrant thing, we're going to actually figure out the quadrant in our first step, and then everything will kind of work after that. We can always find the sine, cosine, tangent of really anything. As far as the inverse trig goes, that kind of restricts our quadrant, but that will be our first step. Now, the inverse secant is negative root 5 over 2. What are the quadrants for inverse secant? 1 and 2. I never like thinking about inverse secant. I'd rather think about inverse cosine. Cosine is 1 and 2, so quadrants 1 and 2. Now, if the inverse secant is something negative, does that mean our angle is a quadrant 1 angle or a quadrant 2 angle? Quadrant 2. So when I draw my triangle, I'm just going to draw it in quadrant 2. Technically, the angle is like this angle over here. We're not really going to make a huge deal about this. This is not a big deal. But if I know that my secant is negative root 5 over 2, I think I know my hypotenuse is root 5, and I'm going to say my adjacent is going to make that side negative 2. I know it's a length of a triangle, should be positive, but because we're going in quadrant 2, I'll say we're moving in like the negative 2 direction.
Your side's 1.
Missing side of the triangle by Pythagorean theorem is 1. Ignore like the negative 2 when you do Pythagorean theorem. Ignore the negative part, really, of the negative 2 when you're doing Pythagorean theorem. If you're not seeing that, root 5 squared minus negative 2 squared equals 5 minus 4 equals 1. Take the square root. We're going to get 1. I want the cotangent of that angle, which means if we're dealing with this kind of shaded in, you called this a reference angle last year. I don't really want to get too much into this, but I'm going to do my adjacent over my hypotenuse. No, I'm not. I'm going to do my adjacent over my opposite. Negative 2 over 1, negative 2. The real reason we went through these two is because these maybe won't show up too much, but the last two are actually pretty important. The cotangent of the inverse sine of x. Does this sort of look like the previous problem, where there's inverse trig inside trig? This is like saying, what angle has a sine of x? Find the cotangent of that angle. I'm going to do this the exact same way I've been doing the other ones. I'm going to draw out a triangle. I'm going to say my angle over there is theta. If the sine is x, sine should be a fraction, though. How do you make x into a fraction? Don't overthink. What's that telling me about how I can label some of these sides? This is honestly the exact same thing we were just doing with numbers, just with variables here. Bless you. Take a moment, find that missing side, and when you're done, find the cotangent of that angle. Go do your adjacent over opposite. Abby, do you have that missing side, the adjacent side? You're close. Square root of that thing. Pythagorean theorem, make sure you take the square root of that side. We will get square root of 1 minus x squared. And Emily, once we have that, what's the cotangent of that angle? Good. The adjacent over the opposite, square root of 1 minus x squared over x. Do you follow how that worked? You try that last one. Secant of the arctangent of x. Draw a triangle where the angle in the triangle has a tangent of x, or x over 1. Find the missing side, and then get the secant. seeing them now. Adam, how did you label the sides of your triangle? Okay. Good. What would the hypotenuse be? Yeah, Pythagorean theorem, x squared plus 1 squared. Take the square root of that. And we've got a triangle. Now I want to find the secant of that angle. Danielle, what do you think for the secant?
I got square root of 1 plus x squared.
Square root of 1 plus x squared, square root of x squared plus 1, over?
It was, I was got that. It was 1 over, like the first side.
So I guess what I'm looking for you to say is, it was over 1, so we don't need a denominator. So that's all we have. Good. Square root of x squared plus 1. The beginning of your homework tonight will be some of this pre-calc review stuff, what we did last time and what we just did. We need to get into derivatives, and we're just going to keep doing notes through here so I can record for those people who are out. We are, let's see, so it is May 8th, and we are looking at section 5.8 in the notes, derivatives of inverse trig functions. These are the final 6 derivatives that we will need to know this year. Which makes sense because it is May. We should be getting near the end. The derivative of the arc sine of x. This is not going to seem obvious at all, but the derivative of arc sine of x is 1 over the square root of 1 minus x squared. I think that looks really weird. You would probably expect some sort of trig or inverse trig in there. There isn't. The derivative of the arc sine of x, 1 over the square root of 1 minus x squared. The derivative of the arc cosine of x is the same thing, just negative. Negative 1 over the square root of 1 minus x squared. We will see in a moment where these come from. I'm going to recommend you write them 2 at a time because, like everything in trig, they kind of come in pairs. The derivative of the arc tangent of x is 1 over 1 plus x squared. And the derivative of the arc cotangent of x, what do you want to guess? The negative of that thing. Negative 1 over 1 plus x squared. Finally, the derivative of the arc secant of x. This one's really weird. 1 over the absolute value of x times the square root of x squared minus 1. And the derivative of the arc cosecant of x, like everything else, is the same thing, just with a negative 1 up top. Yep. I think I'll probably go through the proof of one of these, and then the rest of today will just be seeing how this stuff works, in particular with chain rule involved and that stuff. Did those derivatives make you think of anything else we've done? Do those answers kind of look like anything? You mean like what we were just doing? Yeah, they kind of do. Here's the deal. Let's prove why the derivative of the arc sine of x equals what we want it to equals 1 over square root of 1 minus x squared. I'm going to say that y equals the arc sine of x, and I want to find dy dx. Same thing as saying find the derivative of the arc sine of x. But at the moment, I don't actually know anything about arc sine of x. How could I could do something to both sides to get rid of my arc sine. What would undo an arc sine? What's the inverse of an arc sine? A what? Are you saying a sine or arc sine? A sine, sure. Regular sine would undo that. I can take the sine of both sides, and I can say that the sine of y equals the sine of the arc sine of x. And assuming quadrants and things are good, can't we just say that that right side is just x, as long as we're like in the right quadrant, which will be our assumption here. So I want to find the derivative of this thing. What's the derivative of the sine of y? Be careful. Little careful. Nope. No. Cosine y, dy dx. Regular trig things here. Derivative of sine y, cosine y, dy dx. Derivative of the other side. 1. So the derivative is going to be 1 over the cosine of y. The derivative of the arc sine of x is 1 over the cosine of y. That doesn't seem okay. We shouldn't really have a y in the answer. We should just have x things in the answer. First, are you okay with saying 1 over the cosine of y is the same as some other trig function? In particular, what trig function is 1 over cosine? Secant. This is just saying the secant of y. But again, that's still no good. I can't have a y in my answer. What does y equal in this problem? Julian. The arc sine of x. Our derivative, now we're starting to get there, is the secant of the arc sine of x. That's not what I want the derivative to be, though. I want it to be 1 over the square root of 1 minus x squared. Well, we can simplify this by using our triangles. Let's see, the arc sine of x. So I've got my angle theta, whose sine is x, so the opposite is x, the hypotenuse is 1. I'm just going to kind of fly quickly through this. The adjacent is square root of 1 minus x squared. What's the secant of that angle? Well, the hypotenuse over the adjacent, 1 over square root of 1 minus x squared. All the other 5 can be derived in a similar way. The absolute values come from involving the fact that there are 2 different quadrants where things could work. No, we don't need to know the proof, but we do need to know the formulas, and we do need to be able to work with them. And that's what we're going to take a look at for the rest of the period. We've got to move. Next page. First example. Let's find the derivative of the arc sine of not x, but 5x. Before we even start plugging things in, what rule do you think we're going to need to use here? Chain rule, because there's something inside your arc sine. Okay, so the derivative of the arc sine is one of our new 6 formulas. That says it should be 1 over the square root of 1 minus that 5x thing in parentheses squared. I'll clean that up in a moment. That's the derivative of the arc sine part. What do we need now? Times 5 because of our chain rule. I'm going to clean this up just a tiny bit. I'm going to say this is 5 over the square root of 1 minus 25 x squared. And I have a derivative. I would like you, do you see what I did? Maybe? I would like you to find the derivative of the tan inverse of 6x cubed. Ooh, did I give you the derivative of tan inverse? They are the same thing. Arctan, tan inverse, they're the same thing. They're going to be mixed in the homework. Realize they're the same thing. Go find the derivative, which again makes me think there's going to be some chain rule involved here. Definitely flip back to that previous page. We're not going to have time today, but next class we'll try to get all these things on an index card for you.
Do it at home.
You can certainly do that at home.
3 times 6, 18.
Adam, do you think you have an answer? Good. 1 over 1 plus that thing, 6x cubed squared, times the derivative of that piece, so times 18x squared. I'm going to write this as Adam just said. It's 18x squared over 1 plus 36x to the 6th. Okay, let's try the derivative of the arc cosine of the square root of x. I want to see how far you can get here. We'll go through some of the end simplifying things together, but see what you can do on your own with this one. I hope you are still thinking chain rule. So I have my first step in there. Negative 1 over square root of 1 minus root x in parentheses squared. Jacob, what are we going to multiply this by?
1/2 x.
Good.
1/2 root x.
Okay, so let's see here. I've got negative 1 on the top. Square root of 1 minus root x squared is just x. This thing over here is like a 1 over 2 root x thing. Honestly, I think I'd be okay with this for an answer. We could put them together and say negative 1 over 2 root x root 1 minus x. Are you allowed to multiply those roots together? I think we could. Square root times the square root, we can multiply as long as we multiply the inside pieces together. We can do that and we can say negative 1 over 2 root x minus x squared. That would work as well. Just like saying, can we multiply root 3 by root 7? Sure we can. You're just going to get root 21. It's the same logic down here. Exactly. I think I'd be fine with any of those versions. This one, that one. We're going to move up a little bit. Next, the derivative of the arc secant of x cubed. Go do your derivative. Don't yet simplify things. I've got to talk through some of the simplifying stuff with you. There's a piece that's a little tricky that I need to make sure we see. Okay, 1 over absolute value x cubed times the square root of x cubed squared minus 1 and I'm getting 3x squared over the absolute value of x cubed times the square root of x to the 6th minus 1. Any questions so far? If you get down to this, you'll get all but 1 point. Can I simplify the x squared with the absolute stuff inside the absolute value bars? Does that seem reasonable? Probably not. Can I just get rid of the bars? Is x cubed always positive?
No.
It's not. Would x squared always be positive?
Yes.
Here's what I can do. I think I can write that thing on the bottom as absolute value of x squared times x times the square root of x to the 6th minus 1. What's the absolute value of x squared? Just x squared. We could get rid of the bars around that piece. Could I also get rid of the bars that are around just the x by itself?
No.
No. So I could write this as 3x squared over x squared times the absolute value of x times the square root of x to the 6th minus 1. What good thing does that let me do? Boo.
Cancel.
How about cancel the x squareds? We're going to get 3 over the absolute value of x times the square root of x to the 6th minus 1, and that's as far as we can go. No, we can't move the x inside the root. We're just going to leave it like this.
Just keep things separate.
Something like this I would want simplified down to that line. Okay, I would like you to try something similar now with the derivative of the inverse cosecant. Let's do an e problem of e to the 2x. Deal with your inverse cosecant with the e to the 2x plugged in, and then use your chain rule on e to the 2x. Not yet. Hold on. Not there yet. You're going to multiply the thing I just wrote on the board by the derivative of e to the 2x. Well, the derivative of the e part is e, so e to the 2x, times 2. Really, this is kind of like a 3-part chain rule problem. We dealt with the inverse cosecant. That's this thing. Then we dealt with the e raised to the, that's this thing. Then we dealt with the 2x. That's that thing. Okay, so this is 2e to the 2x over absolute value of e to the 2x. What is e to the... What was that? Thank you. Yep, lost the negative. Thank you very much. Negative 2e to the 2x over absolute value e to the 2x. What is e to the 2x in parentheses squared? E to the 4x squared? No. Power to a power means we just multiply the powers together. So we're just going to do 2x times 2. We're going to get e to the 4x. Not e to the 4x squared. Power to a power, multiply the powers. Minus 1. Let's do some simplifying. The absolute value bars, do I need them?
No.
That thing is always positive. E raised to any power is always some positive number, always above the x-axis. So we're going to say negative 2 e to the 2x over just regular e to the 2x times the square root of e to the 4x minus 1. Negative 2 over the square root of e to the 4x minus 1. Let's take a look at this. The derivative of the arc sine of x over 3, or of 1/3 x. See how far you can get, but I feel like we're going to do some of the simplifying work together. At least take care of the initial line.